Let's dive right into this explainer. Today, we're going to unpack a fascinating and honestly kind of terrifying reality of power generation. We're looking at how microscopic chemical agents, things you literally can't even see with the naked eye, cause massive mechanical failures in heat recovery steam generators, or HRSGs. Look, if you're operating or maintaining a combined cycle plant, understanding this microchemistry isn't just nice to know, it's absolutely vital to the macro survival of your equipment. So what actually brings a massive steel power plant to its knees? You'd probably think it takes brute force to destroy huge carbon steel and low alloy piping that operates under immense pressure and heat, right? But the real culprits aren't swinging sledgehammers. They're actually invisible, microscopic ions quietly navigating through your feedwater and steam systems. And left unchecked, these tiny contaminants systematically dismantle your plant from the inside out. We're talking severe safety incidents, forced outages, and just total catastrophic equipment failure. All right, here's how we're going to break this down today. First, the invisible HRSG threat. Second, the acidic attackers, our anions. Third, the scaly saboteurs, the cations. Fourth, we'll dig into the actual HRSG corrosion mechanisms. And finally, how we go about protecting the power plant. Okay, Section 1, the invisible HRSG threat. In the world of power plant water chemistry, contaminants basically split into two opposing camps, based entirely on their electrical charge. On one side, you have the anions. These are your negatively charged ions, and you can think of them as your acidic attackers. They are the main driving force behind localized acidic conditions, aggressive pitting and cracking in your metals. Then, on the flip side, we have the cations. These are the positively charged ions, your scaly saboteurs. They contribute heavily to hardness scaling, and they form these incredibly thick, highly corrosive deposits right on your heat transfer surfaces and turbine blades. Both sides are completely destructive, but they attack the plant in very, very different ways. Moving on to Section 2, acidic attackers, the anions. Let's see where they come from. What's really interesting here is how these anions usually sneak into the system through just common, everyday operational hiccups. Take chlorides, for instance. A simple cooling water leak in your condenser, especially if you're running seawater or brackish water, and bam, you've introduced chlorides that lead straight to severe pitting and stress corrosion cracking in your stainless steel components. Then you've got sulfates. These often sneak in from raw makeup water, or maybe leaking chemical regenerants from your ion exchangers. Sulfates are notorious for accelerating acidic attacks and under-deposit corrosion. Carbonates and carbon dioxide, they usually show up via air in leakage. Once they're inside, they lower the pH in those early condensates inside turbines, totally setting the stage for flow-accelerated corrosion. And finally, organic acids. These are kind of ironic because they often come from the thermal breakdown of the exact water treatment chemicals meant to protect the system, ultimately leading to localized acidity under high pressure. Which brings us to Section 3, scaly saboteurs, the carcinogens. The crucial thing to understand about cations is how they physically armor themselves onto metal surfaces. Look at sodium. Whether it gets in from seawater contamination or slippage from your demineralizers, sodium loves to combine with chlorides and hydroxides. The result? These sticky, highly corrosive, caustic deposits right on your turbine blades. Then we have calcium and magnesium. If you get a hardness breakthrough in your raw water makeup treatment, these ions react and form a hard, glass-like scale on your boiler heat transfer surfaces. And this scale acts like extreme heat insulation. Finally, iron and copper ions. These are actually the byproducts of corrosion happening elsewhere in the feed water train. They travel, and then they deposit as this dense crud in high-pressure evaporators, causing massive localized overheating. Section 4, HRSG corrosion mechanisms. Let's examine the final blows. First up is flow-accelerated corrosion, or FAC for short. This one primarily goes after low-pressure economizer elbows, piping, and headers. See, your carbon and low alloy steel pipes naturally form a protective metal oxide layer called magnetite. But when you have areas of high-velocity, turbulent water or two-phase fluid flow, that protective armor is literally stripped away. And remember those carbonates and CO2 we talked about earlier? Well, by lowering the pH of the water, they make the environment so much more aggressive, supercharging the FAC process until the pipe wall simply thins right out and bursts. Now let's look at acid dew point corrosion. This builds into a totally different type of threat. Unlike the water side issues we just discussed, this is strictly a gas side attack. It targets your low-pressure economizers and cold end headers. Basically, it happens during startup or low-load operations whenever metal temperatures drop. Sulfur trioxide or hydrogen chloride gases in the exhaust mix with condensed water vapor. The moment the temperature falls below the dew point, these mix together to form highly aggressive acids that just eat right through the external surfaces of the tubes. Next is under-deposit corrosion, or UDC. Honestly, this might be the stealthiest attack of the whole bunch. It happens in the high-heat flux evaporator tubes. Remember that crud formed by iron and copper cations, or the scale from calcine? Well, those deposits are actually porous. Boiler water chemicals like sodium hydroxide seep into those pores and boil off. What they leave behind is a highly concentrated, incredibly corrosive puddle trapped directly against the metal. It just quietly rots the tube away, totally hidden beneath a layer of scale, until, boom, you have a catastrophic failure. And finally, we have stress corrosion cracking, or SCC. This one is absolutely devastating because it targets the most highly stressed mechanical areas of your plant. Places like the steam drums, tube-to-header welds, and transition joints. SCC needs two things to happen at exactly the same time: mechanical tensile stress and a corrosive chemical environment. So if you've got high levels of aggressive chloride anions or caustic sodium cations in your boiler water, they will literally attack the microscopic grain boundaries of the stressed metal. They essentially unzip the steel and split it wide open. So if we pull all this together, we can directly link these exact chemical suspects to the specific mechanical failures they cause. Carbonates and CO2, they set the stage for FAC by dropping the pH. Sulfates, they hide under scale to supercharge UDC. Chlorides and sodium provide the exact toxic environment you need to crack stressed metal via SCC. And those iron and copper ions are the initial architects, building the porous crud that allows UDC to take hold in the first place. Every mechanical failure we're looking at here starts with a chemical imbalance. Section 5, protecting the power plant. Let's talk defense. Thankfully, we have a robust system of defense for this. Industry treatment matrices map out exactly how operators trace specific impurities to dedicated mitigation strategies. For instance, if you're detecting hardness from calcium and magnesium, the matrix dictates treatments like softening, reverse osmosis, or demineralization. If chlorides and sulfates start creeping in, you've got to rely on electrodialysis or distillation. If carbon dioxide is lowering your pH and you're risking FAC, you deploy aeration, deaeration, and neutralizing amines. The absolute secret to plant reliability is rigorous, continuous monitoring of cation conductivity and pH, and instantly applying these exact treatments the very second an impurity spikes. So, it all comes down to this. Do you truly know what invisible suspects are hiding in your plant's feedwater right now? Understanding this micro-level chemistry is the absolute only way to prevent macro-level disasters. You can't just monitor pressure and temperature. You have to monitor the ions. Take a close look at your water analysis logs today. Are your chlorides creeping up? Is your sodium slipping? Because finding out now is the difference between making a simple, routine chemical adjustment and facing a multi-million-dollar forced outage. Thanks for hanging out with me for this explainer, and definitely keep a close eye on that chemistry.